Welcome to The Explainer. When you watch something tumble through the air, have you ever wondered how on earth physicists could describe that motion? It just looks so chaotic. Well, today, we're going to unravel the physics of spin, and we're going to do it by translating it into a language you already speak, the language of simple, straight-line movement. So let's start with that puzzle. Picture it. You toss an eraser, or a football, or really anything with an odd shape. It's moving forward, but it's also tumbling end over end. The whole path just looks like a total mess. How could there possibly be a simple answer for that? Well, it turns out the solution is just incredibly elegant. The secret is to stop looking at it as one chaotic mess. Instead, you have to see it as two really simple movements that are just happening at the exact same time. Here's how it works. First, you can just track the object's center point as it moves from A to B. We call that translation. That's the easy part. Then, and this is the really clever bit, you can separately describe how the object spins around that center point, and that's rotation. When you split them up like that, the problem becomes totally solvable. So today, let's master the spin. Now, just to keep things from getting too complicated, we're going to be focusing on what physicists call rigid bodies. It's a fancy term, but it just means objects that don't bend or squish or change shape while they move. So think of a spinning coin or a meter stick, not, a wiggling cat. And here's what is so incredibly cool about all of this. We don't need to learn a whole new set of physical laws to get a handle on rotation. Nope, all we need to do is build a kind of dictionary, a way to translate every concept from the straight-line world we already know into its spinning equivalent. All right, let's start building that dictionary. In linear motion, we use the letter x to say where something is on a line. For rotation, the matching idea is the Greek letter theta. That describes its angular position, which is just a simple way of saying how much it's turned. Okay, so how should we actually measure that angle? We're all used to degrees, right? 360 degrees in a full circle. But if you've taken a science class, you know that physicists insist on using something totally different, called the radian. So what's the deal with that? Well, for one thing, using degrees can get a little confusing. There's a great story from a professor who had a violinist tell him they'd completely reformed their life by doing a 360, which of course would land you right back where you started. But the real reason physicists love radians is because they make the math just beautiful. A radian is defined in this really natural way that directly connects the angle of the turn to the actual distance you travel along the edge of the circle. This means all the formulas end up being super simple and elegant, without a bunch of messy conversion numbers cluttering everything up. Okay, time to add some more words to our dictionary. So in the linear world, velocity is how fast your position changes. In the rotational world, angular velocity, that's the Greek letter omega, is just how fast the angle changes. And the pattern just keeps going. Linear acceleration has a twin called angular acceleration. That's alpha. See, it's the exact same logic, just applied to things that spin. Okay, so we've translated the language of motion itself, position, velocity, acceleration. But what about the things that cause all that motion? Now we get to the two biggest ideas, the most important part of our whole dictionary, finding the rotational versions of mass and force. In the linear world, mass is basically an object's resistance to being pushed around. It's inertia, right? Well, the rotational equivalent is something called the moment of inertia. We use a capital I for it, and it's just a measure of how hard it is to get something to start spinning or to stop spinning once it's going. And here's what's so fascinating about it. Moment of inertia isn't just about how heavy an object is, but where that mass is located. Think about an ice skater. When her arms are stretched out, her mass is spread out far from her center. That gives her a really high moment of inertia, making it hard to spin fast. But the second she pulls her arms in, all that mass is concentrated, her moment of inertia plummets, and boom, she starts spinning way, way faster. So if moment of inertia is just rotational mass, then what's rotational force? That has a name too. We call it torque, and we use the Greek letter tau. The simplest way to think about it is just as a twist. It's a thing you apply that causes an object's spin to change. And this explains something you already know perfectly well from your everyday life. Why are doorknobs always placed as far away from the hinges as possible? Because pushing there, far from the pivot point, creates the maximum amount of torque. If you try to push a door open with the same force right next to the hinge, well, you create almost no torque, and that door barely even budges. So here is the absolute key takeaway. Torque isn't just about force. It's a combination of two things: how hard you push, multiplied by how far you are from the pivot point. If you want the most twisting power, you have to apply that force as far out as you can possibly get.
All right, we have finally done it. We have all the pieces we need to complete our dictionary. And now that we have this complete translation in our hands, we can finally reveal the single master equation that governs all of rotation.
And look at that. Here it is, our complete translation guide. Position becomes angular position. Velocity becomes angular velocity. Mass becomes moment of inertia, and force becomes torque. Every single key concept has a perfect logical partner in the world of spin. So what does this actually let us do? Well, it lets us take what is maybe the most famous equation in all of science, Newton's second law of motion. You definitely know this one. Force equals mass times acceleration. F equals ma. Now, just watch what happens when we use our new dictionary. We just swap out each piece for its rotational twin. Force becomes torque, mass becomes moment of inertia, and linear acceleration becomes angular acceleration. The legendary F equals ma becomes its equally powerful twin, tau equals I times alpha. It is the exact same beautiful logic, just for things that spin. And that is the payoff. Remember that chaotic tumbling eraser we started with? Turns out it's not a mystery at all. Its entire complex motion is perfectly described by just two beautifully symmetrical laws, one for its straight-line path and one for its spin. So that's our explainer on the physics of spin. You now have the translation guide. The next time you see something spinning, whether it's a planet, a car wheel, or even a fidget spinner, look for the torque that's making it turn and the moment of inertia that's resisting that change. You'll see that it's all governed by the same elegant rules.